So, good day everyone, and happy New Year. And thank you for having me part of your day. Welcome to this math blog episode. You might be wondering that as an agent with temporary license like me, what am I doing while waiting for the permanent license? What keeps me going? We all have our options, and definitely God will help lead us to the best place for us. But again, we are the captain of our own ship, of our own destiny. So my personal decision is to wait. And while waiting, I am validating my existence through arts, blogs, reviewing the Film Life products, and of course, through the nurturing engagements in Facebook and LinkedIn. After having vaccinated, probably I can go back as a customer service specialist or perhaps invest on further studies in math and review depth ed math for more online contents like this. True enough, we all deserve or we all need time and money for a decent higher math for our country. Why? Because we deserve a lot of math educators and scientists, okay, who can help big economies helping in the problem of climate change resolve such global problem by giving a local data. It also has a message of practicing minimalism for a happier life while seeking what is best for the common good. When money is not abundant and savings is just enough, yes, it needs or it takes courageous spirit and heart to keep me going for these priorities and aspirations. And I just have to claim giving back to the community for more math online contents and to help Film Life grow the team of protection champions. And true enough, we all deserve some time for our passions. Sketches, blogs, nurturing engagements in Facebook and LinkedIn to validate our existence and identity. So please continue to support me in my messages of my educating and service. For the belief that the dreamers and advocates of change deserve a quantified scientific research, let me provide to you or discuss a material from George Brown College that describes the trigonometric functions. Yes, this is still inspired from the depth ed curriculum or depth ed LM on geometry. And yes, let's have a sample discussion of a technical document for math. Okay, so upon seeing a graph here, you might wonder, Maan, why are we really describing or plotting graphs for a certain function? Why? Okay, why are we quantifying things, quantifying functions, describing graphs? Let me answer it this way, okay? So, logic and math flourish because we do have great math legends who happen to have time, resources, and capability to answer all of our questions. We do know that we have a lot of questions because we have curious minds who happen to have no time at all in discovering the answers. That's why we have math legends and math contributors. And they do have the mindset that they will document whatever math they have with the idea that it can be useful, it can be applied in the future. And yes, those answers from our math legends and contributors happen to have been useful in many innovations and for the massive undertakings that we are progressing in resolving climate change, for example. So we can then consult from all of those math documentations when the time arises. So that's really the mindset of the pure mathematicians. Okay, so whatever pattern we have discovered We put it into writing, we document it. So here's now the graph or sine function, y equals sine x. So what are its characteristics? So how I'm gonna read, how are we going to explain this document? Okay, so let's start with this statement. Okay, this can be read as the domain is a set of all real numbers. Okay, so why all real numbers? It means that we can have all angles as the input for this sine function. Okay, you're given your input, and as a real number, for this function, it can be expressed in degrees, right? 30 degrees, 60 degrees, 90 degrees, right? Because if we talk about Trigo functions, we describe our input naturally in degrees because angles are expressed in degrees, okay? And these degrees can be converted to radian, okay? And this radian can be converted to numbers. You can refer to my other episodes, a breakdown on how we can convert a number in degrees to radians and into numbers. And why are we converting expressions in degrees to radians and then eventually to numbers? Because tools like Excel and GeoGebra accepts the domain of real numbers as really numbers and not in degree expression or in radians expression. Okay, so that's for domain. And the next for range. So we have -1 and 1. So for all of the real numbers, as your domain or input, the output, so that's the range, the y values, are values between -1 and 1. Okay, set of numbers from -1 to 1. So not all real numbers. That is very much evident from this graph. As you can see, the sine graph, the sine wave here, never goes beyond 1 and -1. Okay? For this function, y equals sine x. And next, the statement period is equal to 2 pi. What is a period then? A period describes the instance of the graph that has been repeated. So for example, this one, this is a whole cycle of the instance that has been repeated. Hello. Okay, so let's continue. We will be discussing period. Okay, so why is it that period is equal to 2 pi? So it is because from 0 degrees, okay, or 0 up to 2 pi, alright, so that's 2 times 3.1416, you have a set of unique points, okay? And this set of points here will be repeated to another period. So an instance, a set of points from 0 to 2 pi will be repeated to another period. So let me describe further period this way. Okay, so if we will consider the unit circle, so you have here 0 degrees, right? And then we were going to increase the angle, and you can see that the graph, okay? And as we increase the angle to 90, okay, then it reached the peak, and then we move increase the angle. Okay, and it's like we are making a circle. Okay, one revolution. So after having one revolution in a unit circle, we also have one period. So the set of points here in one period are all unique. Okay, so you have one unique instance of a period. And we also need to take note that in one period, you'll be considering the range -1 to 1. So the points will just move along -1 to 1. And what will happen if we will make another revolution? Okay, so we'll use this graph, this illustration. So again, I did not create this GeoGebra builds, okay? I've managed to research it in Google. Okay, there are a lot of GeoGebra assets in the internet for illustration so that you can explain it to your learner. Okay, because most learners are visual or are visual. Okay, so we have here one revolution, right? So one period. Okay, and then if we make another instance, another period, okay, with the same set of points, then we are making another revolution of the circle to make another period. So we have here two revolutions in the unit circle. And now we will going to discuss x-intercepts. So what are the x-intercepts? So what is for the function y equals sin x? So what is x-intercepts again? Okay, so these are the points that touch the x-axis of the Cartesian plane. So these points, okay, when y is equal to 0, what are the x's? So we can say that we can get x-intercepts for the multiples of pi. Okay, so as you can see here, we have pi, 2 pi, 3 pi, 4 pi. So if the angle is, the x value is a multiple of pi, then we are getting the x-intercepts. So hope that is clear. And for the y-intercept, that would just be the origin when y is equal to 0. So we can say that the rest of the points in the graph will not touch the y-axis, only the origin. Okay, so going back to the discussion about maximum points, so we have here description again that the peak points, okay, are in the points wherein the y coordinate is equal to 1, and that will happen if the x coordinate is pi over 2 plus the expression 2k pi. Okay, so this 2k pi is telling us, is quantifying the period. Okay, so, and the k would tell us if you are at the first period from the origin, the second period from the origin, the third period. So okay, so to illustrate further maximum points, okay, so we have quantified it by this expression, pi over 2 plus 2k pi, that when we have an x coordinate equal to this expression, our y will be equal to 1. And that's the peak point. Okay, so to illustrate that, so for example, we have this period, the first instance of the period from the origin. So we have not able to complete revolution from the unit circle, right? So we are approaching 1 revolution, okay? So let's go to the peak. So that's the peak. Okay, so we have not completed yet 1 revolution of the circle, so the k there is 0. So we will consider this formula, k is equal to 0, so you have pi over 2. So pi over 2 is 90 degrees. So when the x, the domain is 90 degrees, or pi over 2, and in numbers that's around 1.5. Pi is 3.1416 divided by 2, right? So conversion again, degrees range to numbers, and then you have 90 degrees, so you have the highest point. Okay, and then when we have completed, so we'll be completing 1 revolution here, 1 period. Okay, and now we're going to have another example where the highest peak, okay, the maximum point is at the second period. Okay, so let's illustrate it this way. So we are done here, okay, for the 1 revolution or 1 period, and we will go beyond the 1 period and increase the angle further. That would reach to another elevation in the unit circle that equals to 90 degrees. Okay, so we already have completed 1 revolution at this point, so k now is equal to 1. So we were going to substitute k is equal to 1 to this formula. So 2 times 1 is 2, then times 5, so 2 pi plus pi over 2. So we have 5 pi over 2 as the domain. Okay, and if the domain or the x coordinate is 5 pi over 2 or equals to 7.8, then we have a y equal to 1. Okay, and that's the maximum point, the highest, another peak point or maximum point. So we have completed 1 revolution, so k is equal to 1. And let me stress then that the quantified expression here, 5 pi plus 2k pi is the x and y is 1. It's just telling us that when we have an angle, it can be in the first period or the second period, as long as it creates an elevation in the unit circle that equals to 90 degrees, then we have a maximum point. Now, let's discuss the minimum points. So, when are we going to have the minimum points? The depth of the sine waves. So, looking at this illustration, at this graph, okay, so this is an example of a minimum point. Okay, so we can get the minimum point here when our domain or the x coordinate is 3 pi over 2 and the y is negative 1. So for the minimum points, okay, if we will consider the range of our sine function, we have negative 1 to 1. So obviously, the y coordinate, the minimum point, the y coordinate of the minimum point is negative 1. So when are you going to get y equals negative 1? We'll be getting that if in the unit circle, okay, if the angle that we are considering, the x value, the domain, okay, will provide an angle in the unit circle that is equal to 270 degrees. Okay, yes, you can see 270 degrees. Then we are getting the minimum point. Okay, so that's why it has been expressed by this equation to quantify it. 3 pi over 2, that's 270 degrees plus 2k pi. It is telling us what at what period are you, okay, in for that minimum point. Are you at the first period from the origin, second period, third period? Okay, so if the k is equal to 0, then you are the first period. You have not completed yet a revolution in the unit circle. Okay, so when we were going to go to the second minimum point, okay, 7 pi over 2, so k is equal to 1 because we have completed one revolution. So k 1, so 2 times 1, 2 times pi, so 2 pi plus 3 pi over 2, and that is equal to 7 pi over 2. So 7 pi over 2 will give an elevation or angle in the unit circle is equal to 170 degrees. So each time we translate it to the unit circle and the angle is 270 degrees, then we are getting the minimum point. Alright, and now we will going to discuss symmetry. Okay, so in this documentation, it describes that, let me read that for you. Okay, so since sine negative x is equal to negative sine x, then sine x is an odd function and its graph is symmetric with respect to the origin 0, 0. Alright, so let us now illustrate symmetry together. So we were going to reuse a build that I have created. Okay, so it is in here, this one, a GeoGebra build. Okay, because I already have a classroom. Shout out to my friends, okay, who supported me in offering when I offered online tutorials. So I have built this one already. Okay, so this is a manual creation of data set that would plot the sine wave using GeoGebra. So I have documented, okay, how our learners can create a data set like this so that they can plot the points of the sine graph using GeoGebra. Okay, so we will now going to get the sine values when we have angles which are positive at this instance, and then we were going to negate it so we can check the symmetry. And the formula for this one is a is equal to sine x, where a is equal to 4. Okay, so we will just multiply sine x with 4. Alright, so it returned negative instances of the output here, the y. So this is the domain and this is the range. So when our domain are being negated, the range or the y values are also being negated, or we have also negative values. So we're going to plot that here, okay, so that you can view a symmetry. Okay, so we will just call this two and these coordinates here to make a point. There you go. Alright, so this points now is symmetric to this first set of points. So this is when the function has domain that are positive angles, and then this is a function where our domain have negative angles. Alright, so I just want to reiterate again the steps of checking if the function is has symmetry or not. Okay, like the function sine x. So first, we will going to negate the set of x points or domain, negate those domain values, and then compute for y using the function. And then park the answer if it's negative or positive. And the other side of the equation, or step number 2, you're going to compute for y using positive x values, and then after computing for y, negate it, okay, and see if you still have negative values or not. So you will compare the two sets of y values and see if those two data sets are equal. Okay, and lastly, for the sine function, okay, we have a description regarding the intervals of the increase and the decrease. So it just simply, this documentation here, or this description here is telling us that the sine wave, okay, will have an upward stroke or an increase from 0 to 90 and 3 pi over 2 to 2 pi. And it will going to have a downward stroke or a decreasing pattern from 90 to pi, and then pi to 3 pi over 2. And then for better appreciation of this technical documentation, okay, so let's discuss for a while asymptotes. Okay, so asymptotes, we don't have asymptotes in sine graph or cosine graph. So we have asymptotes for the tangent function, for the cotangent, and then secant, and the cosecant. So if you will compare sine, cosecant with those functions, you can see that there's like broken lines there that describe boundaries. Okay, right? So those are the asymptotes. Okay, and asymptotes, I have described it personally. Okay, in here, these are broken lines, vertical or horizontal, wherein points of a function approaches those lines but never touches those lines. So those are asymptotes. Alright? Okay, so I hope that you have a better appreciation about the documentation gathered in describing the graphs of the 6 trigonometric function as memory aids. And I would still challenge our learners, okay, to create a table like this one, okay, for them not to memorize the formula and what have you. If they will just keep on associating themselves with these values and numbers and these formula, these ratios here, they would realize that trigonometry is so elementary, okay, as an element of algebra. So thanks again for watching, guys. Bye now.